Welcome back. This is Mrs. Gabriel. I'm going to go over Chapter 12, the very end of it, where we just focus on nuclear energy. Remember that as something that's in Chapter 12, that means we're talking about something that is finite, that will run out. It is a non-renewable resource. So when we talk about nuclear energy, we're talking about a couple different things, nuclear fusion and nuclear fission. So nuclear fusion is a reaction that powers like the sun. We're not very good at controlling that yet. It would be great if we were. And then there's nuclear fission, and this is what powers our nuclear power plants. This is what we're going to be spending our time on. So we're going to start by looking at a few pieces of videos that are on YouTube. This one's called Seconds from Disaster, the 2014 series called Seconds from Disaster, and this episode is focusing on the meltdown that occurred in Chernobyl. As you can see, it's a 45-minute video. There is no way that I'm going to record something that you can just look up on your own, but I'll just give you a little piece of it. It's a great video to watch.
War is about to crumble.
The worst case scenario in any nuclear power station is that there's a build-up of heat and energy that becomes critical.
Still, investigators don't understand how the overheated core triggered the final explosion. 56 seconds before the blast, the turbine operator gets the order to proceed with the safety test. He shuts down the turbines. Suddenly, the dials show that the energy levels in the reactor are soaring dangerously high. Now, there's no time left. From disaster. A safety test at Chernobyl has turned into a catastrophe. The nuclear reactor is going to blow in just 13 seconds. And the men in the control room are helpless. Extreme heat ruptures the fuel rods. The blast generates a huge force of pressure against the reactor's 2,000-ton lid. 8 tons of highly radioactive debris explodes into the sky. Nothing like this has ever happened before. Radioactive fuel fragments explode directly into the atmosphere. Investigators calculate that they shoot more than half a mile into the sky. Some of the radioactive material is light enough to be carried by the wind and spreads over thousands of miles. Within 10 days, it reaches as far as Japan and North America.
Radioactive atoms are very unstable and they want to settle down. They do this by spitting out radiation. And if the dose of radioactive material is large enough, then the radiation emitted can be damaging to human tissue or even lethal.
Investigators now know what caused the explosion, but they are horrified by the prospect of a much bigger crisis.
You're going to have to watch the rest of that video on your own, but that's just to give you a piece of why so many people environmentally and from a human health standpoint are very concerned about us using nuclear power in the United States. Now, there's another video online. It's through Crash Course. This guy has tons and tons of awesome videos, and I can't show you all of this either. He's really, really excellent at getting right to the point, very succinct, and he talks about the differences between fusion and fission. If I have time at the end of this little just reminder of what you need to know, I'll add a little of it to the end. So fission is what's used in the process of nuclear power plants fuels. So uranium is fissionable. You need to remember that, fissionable. And the difference between fission and fusion. Fission is when we split into 2 or more parts. We split into 2 or more parts. This is just one of many different pictures. I'll show you more. You can also go on to the PHET animation. Just type this in and look up half-lives online. I'm going to show you a couple screenshots. You need to understand how we calculate for a half-life. and you need to understand how a nuclear reactor works. So that video gave you a piece of the meltdown and what the result of the meltdown was. But the meltdown happens because of these control rods and because of the fuel cells that are in here, in this structure. So as you recall, when I showed you the picture and diagram of the coal-powered electrical generating plants, we had a little boiler, and the boiler was what was firing up our coal, causing combustion. The result of the combustion gave us heat, and then the heat created steam, and then the steam and the kinetic energy from the steam made the turbine move, and then the turbine then helped power the generator, which created electricity. A nuclear reactor still creates heat that then generates steam and turns a turbine. So very similar through that process. But this beginning stage, we have the nuclear fuel rods, and that's uranium, and we put them into pellets, and they sit in the core. The control rods go in and out, and you saw a little bit in the video of that. They go in and out of the reactor, and they make sure that the energy is stabilized the whole time. So I'll show you a little of that in the other video. You can watch some more of it in the video that I just showed you, but you must remember we have fuel rods. The fuel rods are what hold the nuclear fuel, which is in pellet form. And then we have the control rods, and the control rods go in between the fuel rods to absorb excess neutrons. So this is what's controlling the fission reaction. Remember, fusion is with the sun. Okay, now I'm showing you a map. This is not in your book, these extra pictures. So I'm showing you a map here of a couple different things about nuclear power plants and their history in the United States. So if you look to the right in blue, we're looking at what we previously considered for dumping our nuclear fuel once it was not powerful enough for us to use as for energy in a nuclear power plant. Now remember that energy does not necessarily have to do with that radiation that can harm human health and even other animals and plant health. And if you look really carefully, the black are the sites that we considered for dumping our nuclear fuel. The only site that's somewhat under consideration is over here in Nevada, and that's in the Yucca Mountains, which is just north of Las Vegas. What's interesting about this is that we don't have any nuclear power plants in Nevada. So you knew this guy. I don't know why anyone would ever hire him to work in the control room of a nuclear power plant. Meltdown waiting to occur. This is the Yucca Mountain. A lot of this has already been constructed, but we have not allowed this to occur. So the idea is, out of over 100 power plants, once we use up our uranium in its useful form for generating electricity, it is still very, very potent and poisonous to human health due to the radiation it gives off. So the idea is to ship all the uranium or truck it or put it on a train out to the Yucca Mountains, where it is then processed on site, and then it goes through the tunnels and it goes real deep into the mountains, and they think geologically this is the safest place for it to be. A lot of people that live on the pathways to go from the East Coast all the way out to Nevada don't want that truck or that train coming through their neighborhood, having an accident, and then causing the uranium to leak into their groundwater, into their air, and causing radiation poison to them. These are the current operating nuclear power reactors in our country. Notice the Yucca Mountains in Nevada. Not one nuclear power plant. So Nevada is very opposed to, as they say, us dumping into their backyard with our waste. Now, why do we have so many on the East Coast? Well, hopefully you're figuring out, oh, that must be because we have a lot of people living out here. We are definitely more highly concentrated in our U.S. population, all where you see those nuclear power plants. Lots of energy. So the one that you're most familiar with, I think, should be the one that you looked up recently when you had to look up your electric bill and your zip code, and you had to figure out where you got your energy from. So a lot of people around Harford County still think, oh, we probably get all of our energy from the Conowingo Dam. The Conowingo Dam is right here along the Susquehanna River. So down in this portion of the map is Susquehanna State Park, and a little further south of here would be Havre de Grace. Okay, Bel Air would be more in this direction. So this is Route 1, this is the Conowingo Dam. We go further up the Susquehanna River, and bam, there's where our nuclear power comes from. So we get ours from Peach Bottom nuclear power plants. I couldn't get many pictures of it to steal from the internet, but this is one of them. This is Peach Bottom Nuclear Power Plant. Much of our electricity in Harford County comes from here. And this is where they have to put their waste. So they eventually have to store it underground on facility. This is still nuclear waste. This is still something that could be used for a weapon, and it's still something that could eventually leak into groundwater or into the air if it's not very carefully monitored and very carefully kept in conditions that will not let leaks occur. So they have to have security on site to watch this, and they have to make sure that they're constantly watching it. Now, that PHET website, you can do animations to understand a little more about the half-lives of an important material such as uranium. So this shows you just an example about how half-lives work. You're definitely going to need to answer questions like this. These would be considered like math and data, but all you have to do is pay attention right now to just these pictures and you might be fine. If you need a little more help, go to the website and figure it out. So take a look at the chart and you'll notice on the chart half-lives. There's 1, 2, 3 lines for half-lives. Half-lives means it's every time the material has dropped to 50% less. 50% less. So we start here with 100% uranium. And to go through one half-life, that means that we have to only have, I think that's uranium-235, we can only have 50% of what we originally started with. So, moving ahead, we're close to 50% of the uranium, it's 238, uranium-238 is gone. So once 50% of the uranium is gone, we have now reached one half-life. One half-life on this chart is 4 billion years. The uranium-235 that we referred to in your book is a little over 700 million years for one half-life. But guess what? Uranium is hazardous to human health. It's poisonous to human health. It will really, really mess with your thyroid, and it will give you cancer. Uranium is harmful to your health for 10 half-lives. Now, in this case, that's one half-life of 4 billion years, then another half-life of another 4 billion years. So we've gone from 50%, we cut that in half, that's another half-life, so we're down to 25% of the uranium left. That's 4 billion more years, or a little plus. The uranium-235 in your book, to go through 2 half-lives, would be 700 million plus another 700 million half-lives. But human health is at risk for 10 half-lives of uranium. So think about how long that is. So we've got to store this stuff for 10 half-lives, this stuff that we use for fuel. Now, to go through 3 half-lives, what percent of the uranium is going to be left once we finally only have enough uranium to have 50% of it again, half of it again gone? Hopefully you figured out. We're going to go through another 4 billion years in this scenario for this chart, and we're going to have 25%, and then we're taking half of that 25%, which is actually 12.5%. We can go through 4 half-lives, which is going to bring us to 6.25%, and so on and so on and so on and so on. So remember, uranium is to go through 10 half-lives. Now, the other things we have to consider are not just the uranium pellets, storing them very safely and snug away. We also have to consider all the other stuff that has been exposed to that, such as the clothes that people wear, and those are considered low-level radioactive waste. The tools, the rags, and other equipment just with plant maintenance. But the high-level radioactive waste and the low-level right now is stored on site at each nuclear power plant. So we have over 100 nuclear power plants in our country that are storing nuclear waste on site. So there are advantages and disadvantages to nuclear energy. Make sure that you know what is and what is not. But the big reason we use it is because it is cleaner. We don't get any air pollution from it, and that we're not going to be reliant on other countries. So politically and economically, that could be beneficial for us. But the disadvantages are huge, and you can see more of that in the videos. Now, I'm not going to read these to you. These are in your book. You can zoom in on the video if you'd like to study them. But here's the type of things that you should know. You should be able to look at the advantages chart, and you should recognize by covering this up, cover all of these up, and then guess which advantages are these. Which disadvantages are these? Which pollutant, or you can say which pollutant is associated with coal, and then you should be able to answer these. So quiz yourselves on them, make sure you know them. So that's it with what we were looking at as far as nuclear fuels. I'll end this with just a little bit of an introduction to our nuclear chemistry guy so you can get a taste of what you can watch on your own.
There are two general types of nuclear reactions, fission and fusion. Fission occurs when a large nucleus splits into two lighter ones. Fusion is the opposite, when two light nuclei join together to form a heavier one. In both cases, the products of the reaction are more stable than the starting materials, and this is, as always, what drives the reaction. This is a graph of the binding energies of various elements compared to their mass numbers. Elements with very high binding energies, such as iron-56, are very stable and rarely undergo nuclear reactions, but elements with lower binding energies can react much more readily. If the nucleus is heavier than iron-56, it will tend to break into two or more smaller nuclei, a fission reaction. If it's lighter than iron-56, it will more likely participate in a fusion reaction, joining two nuclei together to form a heavier one. But the most important thing to notice here is that with both fission and fusion, stability increases as a result of the reaction. Fission is the type of reaction that we use more often because it's the one that we're better at initiating and controlling, at least so far, and whether it's used in power plants or bombs, the most common fuel for fission is uranium-235. There are several ways that it can react, but the reaction is almost always triggered by hitting uranium with neutrons from another source. When that happens, the uranium splits into smaller atoms. One such reaction produces krypton-92. Yes, krypton is a real thing, along with barium-141. Three free neutrons and lots of energy. This energy is released mainly as the kinetic energy of the escaping particles, which is immediately transferred to the surroundings as heat. Some energy is also released in the form of electromagnetic radiation, such as visible light, X-rays, and gamma radiation. Nuclear power plants use the energy released by these reactions to convert water to steam, which then is passed through turbines, spinning a generator, powering cities and stuff. Because of the enormous amounts of energy these reactions can release, nuclear power plants can potentially produce lots of electricity. But there's also, I think you may have heard, some serious drawbacks. For one thing, as you know, atoms rarely exist in isolation. We write the equation of a fission reaction as if it's just one atom, but in reality, that one atom is surrounded by many, many more. And if one little neutron can trigger the reaction, and that reaction liberates three more neutrons, well, I think you can see where this is going. If the reaction isn't controlled, each reaction triggers three more, and every reaction releases the same amount of energy, which adds up fast. This is pretty much the definition of a chain reaction, and it is the basis of the remarkable power of a nuclear weapon. The same type of reaction occurs in nuclear power plants, but those reactions are controlled in several ways to keep them from getting out of hand. The fact is, these chain reactions have the potential to produce far more heat than the plant can use, so much more that the temperature can easily rise to dangerous levels, enough to melt the uranium. This is the meltdown that you hear about, and most reactor cores are immersed in water to disperse the heat and prevent this from happening. But that's not enough on its own to control this thing. If the chain reaction is allowed to run freely, no amount of water can remove the heat fast enough to prevent a meltdown. The real way we control nuclear reactions is with control rods. They're made of materials that readily absorb neutrons, and they're inserted between the fuel rods of uranium to slow the neutrons down and therefore slow down the reaction. Can be put in more to slow the reaction more, lift it up more if you need more heat. Now, the other sticky wicket of fission reactions is the stuff that's left behind. These reactions not only produce products that are still radioactive, they produce tons of them, lots of different troublesome kinds. Like we saw last week, uranium undergoes many different types of nuclear decay, so not only does each uranium atom produce isotopes of krypton and bromine, but that process also produces many other isotopes of other elements. And as these various nuclei break down, they release more neutrons and more unstable products, and the process continues for a long time. All these reactions eventually yield stable products, but they have half-lives ranging from a few years to tens of millions of years. The products with shorter half-lives stabilize pretty quickly, but they release particles and energy like crazy during that time, so they're extra dangerous. The ones with longer half-lives decay more slowly, release less energy, but that means it takes a very, very long time for them to stabilize. So long, in fact, that for human purposes it may as well be forever. That means there'll always be an issue in our environment, which is why we're always looking for ways to store them and keep them out of our way. Fusion reactions, as you'd expect, are very different from fission. For one thing, the energy released in many fusion reactions.
Okay, so you can watch this video on your own to learn a little bit more about fusion and fusion reactions. We are always working towards trying to control. This would be a much cleaner and more powerful energy for us. So this is the rest of Chapter 2 presented to you by Mrs. Gabriel. That's the end of it. Good luck on your test.